Okay, in this lecture we're going to look at how to calculate the vector product. Now this is of course a way of multiplying two vectors together that gives you an answer that is a vector, not a scalar. Now since the answer for the vector product is another vector, it's going to have both a magnitude and a direction. And we're going to have to be able to calculate both. We're going to have to be able to calculate the magnitude, and then separately we're going to end up needing to determine the direction of this resultant vector. We're going to begin by considering the two vectors that I've shown here. So we have this vector A and this vector B. And you can see that A and B span this parallelogram. And if I drew a line along the diagonal of that parallelogram, that would be our vector sum, A plus B. That's not what we're going to do. Previously, we also looked at the scalar product, and we said that the scalar product would be determined by the length of one vector times the projection of the other vector onto it. So in other words, the B vector is projected onto the A vector, and that length times the length of A would be the magnitude of our scalar product. But what we're going to do now is the vector product, and its magnitude is given by the base, which in this case would be A, times this red line, which would be the height, and that red line indicates the vertical component of B, or the component that rather I would say it's perpendicular to A. So rather than taking the parallel component like we did in the scalar product, we're going to take the perpendicular component. And if we look at that, we can see that that's actually got a geometrical meaning. This red line here, that is actually the component of B that's perpendicular to the vector A. And so if we see that this is a right triangle here, we know that that's the opposite side to the angle between the two vectors, and so that is going to be equal to the magnitude of B times the sine of theta. And so that's also what we can see from the parallelogram. This would be the base, and this red would be the height. The base times the height, that's the area of the parallelogram. And this is going to be essentially what is meant by the magnitude of the vector product. It's the area of the parallelogram that's spanned by the two vectors. And in equation form, we can note that that's going to be A times B times the sine of theta. That is the magnitude of A, or the length of A, times the length of B, times the sine of the angle between them. With the scalar product, it was like the cosine, but with the vector product, it's the sine. So if I give you a problem and I say, here are two vectors, what's the area of the parallelogram spanned by those two vectors? You're just going to take the vector product and get its magnitude, because that's what the magnitude of the vector product means. It's the area of the parallelogram. Now, more often than not, we're going to write it in this equation form here, and so we can say that the scalar product is AB cosine of theta, the vector product is AB sine of theta. Now, those are very similar, and so you want to be very careful not to mix them up. Now, once you have the magnitude of the vector product, you need to find its direction. And the way you get the direction is via the right-hand rule. And I've got a picture here that I stole off the internet, and the picture has the approach for finding the vector product. So what you do is you make your hand in a sort of karate chop shape with your thumb extended at a right angle. You line your fingers up so that your fingers point along the arrowhead of the first vector. And so if I want to form the vector product of A crossed into B, and that's how you read it. The symbol here is called a cross, and that's why the vector product is also sometimes called the cross product, just FYI. So if you hear me say cross product, it's just another word for vector product. So if I want to do A cross B, I line my fingers up with the A vector, and then I rotate my fingers so that they line up with the second vector, which is the B. And so A cross B, you line your fingers up with the first one, and you rotate them towards the second one, and then your thumb extends in the direction of the cross product, or the vector product. Now, this means that the cross product, or the vector product, is always going to be perpendicular to the plane that A and B are in, the original two vectors. Now, one thing that's tricky, if I want to do the vector product, I have to line my fingers up so that when I curl them towards the other vector, it's like I'm closing my fist. And so if your fingers are oriented in the wrong way, your fingers may curl in the opposite direction or a different direction from what you want. So what you'll need to do is, before you curl your fingers, you need to rotate your wrist, if necessary, so that when you curl your fingers from the first vector to the second, that they curl naturally and you can line them up. And so here's a summary again of how to do it. So what you want to do is extend your hand in this karate chop shape with the thumb extended at a right angle. You want to line your fingers up with the first vector. You want to rotate your wrist so that when you make a fist, your fingers will curl towards the second vector, and then your thumb will point in the direction of the cross product, or the vector product as we like to call it. So putting these together, we have the complete picture of how to form the vector product. So the vector product of two vectors A and B is defined such that the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. And by the way, that's always the small angle. If these are my two vectors A and B, there's two possible angles. There's this big angle and then there's this small angle, and you always want to use the smaller angle of the two. So here we have an example. We want to calculate the direction of the cross product for these two vectors. Now, both of these vectors are in the plane of the board or the screen that you're watching this on. And so that means the answer is either going to be into the board or out of the board, into the screen or out of the screen, because we know that the answer has to be perpendicular to the plane formed by these two vectors. Now, let's form the vector A cross B. And so what you're going to want to do is you're going to first line your fingers up with A, and again your hand's going to be in that karate chop orientation with your thumb extended at a right angle. Now, if I am pointing my fingers from the bottom to the top and my thumb is extended towards out of the page, if I try to curl, my fingers are going to curl away from B. And so in other words, if my fingers are pointing this way and my thumb is coming out of the page, when I try to curl my fingers, if this is my right hand, my fingers are going to curl that way. And that's the wrong way. I need my fingers to curl like that. So in order to accomplish that, I would have to actually turn my hand upside down so that my thumb pointed into the screen. Then, if my fingers are pointing along A and I rotate my wrist so my thumb is pointing into the screen, my fingers will then be able to freely curve and line up with the B vector. So that orientation is what is necessary to curl your fingers from one to the other, and that tells me that my thumb is pointing into the page. And so the answer for the direction of A cross B would be into the page. And so that's going to give me that direction. Now I'm going to redraw these vectors here. So if I have these vectors A and B, and I want to form B cross A instead, how would that work? I want to form the vector B cross A. And so first thing I'm going to do is line my fingers up with the B vector. Now if I line my fingers up and I have my thumb extended at a right angle, karate chop style, and I have my fingers such that my thumb is pointing out of the screen, away from the screen towards your face, then I can freely curve my hand towards A and line my fingers up with A. So I want my fingers to be able to curl this way, like that, curl around there. And so if I have my fingers lined up with B so that my thumb is pointing out of the screen, I don't even have to rotate my wrist in this case because my fingers will naturally curl in that direction. And so my thumb is pointing out of the screen, and that tells me that B cross A is going to be out of the page. Now, incidentally, we have a way of notating these two different options, into the page and out of the page, and let me pick a different color so that it stands out. So if I want to represent a vector that's pointing into the page, I represent that with a little X, and usually I'll draw a circle around it, although most people don't do the circle, but I like to draw the circle. You can choose to do it or not. But the X represents a vector pointing into the page or into the screen or into the board. And for a vector coming out of the page, like the one down below, that's represented by a point. And again, I like to draw a circle around it. Now, if you think of the vector as being an arrow, imagine a vector coming out of the page. You're seeing the arrow tip. The head, the point of the arrow is coming out of the page and it's going to hit you in the face. That's not pleasant, but that's the way to remember it. Whereas if you see the vector going into the page, that's like you've shot the arrow away from you and you see the feathers going off into the distance, the feathers at the end of the arrow. And so it kind of gives you a mental image to help you remember which way is pointing in which direction. But the X's, again, are into the page, like the feathers going away from you, and the dot represents the tip of the arrow coming towards you, so that would show how to represent a vector coming out of the page. Now there's one very interesting consequence of this, and we can see if I look at vector A cross B, that's into the page. But when I reverse it and I do vector B cross A, that's coming out of the page. That's interesting. The order that you do the vector product matters. And in fact, one of them is into the page and the other is out of the page. That means they're directly opposite each other. Or another way to say it is the vector flips. So if you do the vector product or the cross product in one order versus another order, you get a 180-degree flip. That's a negative sign added to the vector. In other words, you can say that A cross B is equal to negative B cross A. The order you take the cross product in, or the vector product in, it absolutely matters. And in fact, when you have this situation where when you reverse the order you get a minus sign, mathematicians would say that this is anti-commutative. Anti-commutative. So that is a mouthful, but that's what that means. So we can contrast that with the scalar product. So if I write up here at the top, if I write A dot B, and of course that would be the scalar product, that's equal to actually B dot A. We showed that in a previous video. And so that is an example of an operation that follows the commutative property. The order that you do it in doesn't matter. So you can reverse A and B, A dot B, B dot A. When you're doing the scalar product, the order doesn't matter. But when you're doing the vector product, it absolutely does matter. And in fact, you get the minus sign. So let's do a quick example. I've got two vectors. One has a magnitude of 6 units. The other has a magnitude of 4 units. They're connected tail to tail, and they have an angle between them of 30 degrees. The question is, what is the area of the parallelogram they span? Well, that's easy. We've already said that's going to be the magnitude of the cross product, and we already know how to do that. It's simply A magnitude times B magnitude times the sine of the angle between them. If you plug in the units and the numbers, you get 12 units squared. So that's 6 units times 4 units times the sine of 30. 6 times 4 gives you 24. Sine of 30 is a half, so that ends up with 12. I've got units times units, so that gives me units squared as my dimensions. Now, we want to look at applying this approach to unit vectors just like we did with the scalar product. If you remember, when we looked at the scalar product, we looked at how to use the definition and apply that to different unit vectors. So x hat cross x hat cross y hat, x hat cross z hat, all the possible combinations. How do we do that? So let's consider crossing or taking the vector product of a unit vector with itself. For example, x hat cross x hat. So we know from the definition that the answer is the magnitude of x hat cross x hat is going to be x hat magnitude times x hat magnitude. Those are each 1 because these are unit vectors, times the sine of the angle between them, which is 0. The sine of 0 is 0, so that means that x hat cross x hat is 0. And remember, we can write that as the 0 vector, because if it's a vector on one side, it's got to be a vector on the other side. Now, when you look at the magnitude for x hat cross y hat, and this applies to any unit vector that's not itself, so x hat cross y hat cross z hat, whatever, this is always going to work because they're all mutually perpendicular. They all are 90 degrees apart from each other. X hat cross y hat is going to be x hat magnitude times y hat magnitude times the sine of 90. All 3 of these things are 1, so that's going to be a magnitude of 1. And then by the right-hand rule, so remember, I've drawn this in perspective. So this x hat, it's really coming out perpendicularly out of the screen. And so if I line my fingers up coming out of the screen, and I rotate my wrists so that when I curl them, they curl flat with the screen and line up along y, my thumb is going to point up. And so it points along the direction of z. Its magnitude is 1. So a vector that points in the z direction and has a magnitude of 1 is in fact z hat. And so any 2 unit vectors that you cross together, you're either going to cross it with itself and you'll get 0, or you'll cross them with another vector and you'll get the third, because the answer is always going to be perpendicular. Now, whether it points in the positive direction or the negative direction, that's what you're going to have to figure out using the right-hand rule. So let's consider taking the cross product of 2 complete vectors a and b written out in their component form. And what we're going to do, again, just like we did with the scalar product, we're going to take this first term and we're going to FOIL it out. So I'll cross it into that, in that, and that, and then I'll take that term and I'll cross it into all 3, and then I'll take this term and cross it into all 3. And what I'm going to end up with is 9 possible terms. And so what you're going to see is this is the result that you get. You end up with ax bx, so this is ax x hat cross bx x hat, so that's that first line here. And I factor out the scalar parts, ax bx, and I end up with x hat cross x hat, which we know is 0. So that term goes away, it turns to 0. But if I do ax by, so I'm going to the next level, so I'm starting at ax and I'm multiplying it to by hat, I get ax by times x hat cross y hat, and this is equal to z. Now, the third thing that you need to do is then keep going, and I'm going to cross ax hat with bz hat, ax x hat with bz z hat, and that gives me ax bz x hat cross z hat, and that's negative y hat. And so again, if I line my fingers up with the x, which is really coming perpendicularly out of the screen, and I rotate them so that my fingers curled towards the z, my answer is going to point in the opposite of y hat, and that's going to give me negative y hat. And so please try that and make sure that you see it and you understand how to do it. This is a very common test question that I offer on my tests. I'll give you some unit vectors. I'll say y hat cross x hat and z hat cross y hat and x hat cross z hat. Tell me what they're equal to. And you have to be able to see it in your imagination and do the right-hand rule. So you need to verify each of these 9 terms and make sure that you understand how they are. Why is z hat cross y hat negative x hat? That's what you want to figure out. If you cannot do that, if you don't see how to do that, then you need to come see me during my office hours, and I will sit down with you and show you how to do it. But hopefully this is clear, and you'll be able to figure it out. And once you get it, once you see how to do it, it's super easy. It's literally something that should be free points on the test because it's so easy once you see it. Now, if you don't see it, it's impossible. So let me help you if you need help with this. So once you multiply all of those 9 terms out and you eliminate the ones that are 0, you can group together all the other terms according to which unit vector they go with. And when you do that, you see this pattern. AYBZ minus AZBY, so notice none of these are x, times x hat. AZBX minus AXBZ times y hat. Notice none of these are y. None of these are z, but they go with the z hat. This pattern shows up in mathematics so much that mathematicians have created a very compact way of notating it and calculating it. And I'm going to show you that in the next video.